So last class we talked about the definite integral and Riemann sums and sort of computing the definite integral through a kind of a very geometric method using the idea of limits. Today we're gonna run through some properties of definite integrals. And then we're going to talk about the fundamental theorem of calculus, which is the thing that allows us to compute definite integrals efficiently. Um, Unfortunately, Riemann integration, while it is a method of integration that is valid and sometimes the only way that you can do things, it's not a very computationally effective method to do by hand. So we'll talk about some more computationally effective methods. So recall from last time that our definition of the definite integral was that the integral from a to b of f of x dx is equal to the sum from, or the limit as big N goes to infinity of the sum from n equals 1 to big N of f of x of n times delta x, where uh, delta x is equal to um, b minus a divided by n, and x sub n is equal to a plus, big N, a plus little n times delta x. That was our way of sort of just parameterizing things so that we could make a pretty efficient way of writing out these series. Um, Note that the notation for the integral actually derives from the notation for the sum. This wavy thing here, the integral symbol, it's actually a stylized S. From sum, as in like the summation, the sigma there, right? And this dx, this differential, in some way is derived from delta x, right? If we take the limit of delta x, in other words, dx is equal to the limit as big N goes to infinity of delta x, right? These delta x's are changes in x that have some width, right? And dx is an infinitesimally small change in x, right? So basically, as we let big N get infinitely large, we're taking smaller and smaller and smaller slices, smaller and smaller and smaller little rectangles, right? And so that's where the delta x, the meaningfully sized change in x, turns into dx, which is an infinitesimally small change in x. All right. So we have a handful of pretty nice properties for definite integrals that are good to know. So property number 1. Okay. The integral from a to b of f of x dx is equal to negative the integral from b to a of f of x dx. So integrals mostly make sense, like the intuitive sense behind an integral should come from should make sense when the bounds are the correct way around. Generally, a is always smaller than b, right? A is the lower bound, b is the upper bound. If we reverse the bounds, we end up flipping the sign on the whole thing. Basically, if we integrate backwards rather than forwards, we end up with a negative number instead of a positive number. You can check this through the definition. It's a pretty straightforward. It's a pretty straightforward substitution. So, second, the integral from a to a of f of x dx is equal to 0. This one, we don't even actually need the definition, though the definition does also tell us this. Um, the integral from a to a of f of x dx is a area underneath a curve with width 0, right? What's the area of something with 0 width? Well, it has to be 0. The integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx. Again, just like property number 1, this is a pretty straightforward proof by the distributive property. If you're multiplying every single term in that sum by c, then you can pull the c out front of the sum, and then the c can come out front of the limit, and we get c times the original integral. Similarly, okay, the integral from a to b of f of x plus or minus g of x is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Sorry, plus or minus. So once again, the sum of two integrals will be the integral of the sums. Once again, this is a pretty straightforward application of basic arithmetic properties. Another more geometric property, we have the integral from a to b of f of x dx. That's equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx, where c is any real number. So this one is very obvious geometrically when c is between a and b, but it's actually still true when c is not between a and b. It still works out geometrically if you actually sit down and look at the areas, but it's more clear if c is between a. I think basically what you're doing is you're cutting the area in half somewhere, or not in half, but you're cutting it down. You're cutting it somewhere, and then you're saying, okay, well, the area of the two parts is equal to the area of the whole. And our sixth property here, this one is not super important, but it is just something that's worth noting real quick. The integral from a to b of f of x dx is equal to the integral from a to b of f of t dt. And if a and b are numbers, or constants, both of these are constant as well. If you just change the variable, it doesn't actually change anything that's happening there. And in general, you should expect, if your bounds are numbers, you should expect your answer for a definite integral to always be a number. Okay. So these properties, we can use them to sort of join integrals together. I could feed you a bunch of sort of canned examples of like weird ways in which they work, but I think it's going to be more obvious how we use them once you start actually using them in practice. So I'm going to lay off doing a bunch of examples with the properties. And instead, I'm going to get to the punchline of integration, which is the fundamental theorem of calculus. So I think very early on in the semester, I mentioned the fundamental theorem of the calculus. I think on the very first day, actually, when I was talking about what calculus is. This is the thing that Newton and Leibniz both independently found that and wrote a theory around that results in modern calculus today. This is the bridge between differentiation and integration. And there are two parts to it. The first part is sort of the theoretical part. It's the part that's kind of in a holistic sense and a theoretical sense to the field of calculus as a whole. It's the really important part. Okay. So part one says that, and this is not the exact version of the fundamental theorem of calculus. Technically, you can do a little bit better than this, but that's okay. We'll just use this version. If f of x is continuous on a to b, and big F of x is equal to the integral from a to x of little f of t dt, then big F of x is also continuous on AB and differentiable on open interval, and the derivative of f of x is equal to f of x. The derivative of big F is equal to little f. Alternatively, if you prefer, and somewhat more compactly, the derivative of the integral from a to x of f of t dt is equal to little f of x. So the fundamental theorem of calculus, what it's saying in a sense, is that integrals and derivatives are inverses to each other, kind of. They're not perfect inverses to each other, unfortunately. There is some information lost in the transition. We're not going to get everything back when we differentiate. If we anti-differentiate or take an integral and then redifferentiate, we don't necessarily get everything back. But this theorem says that somehow derivatives and integrals do undo each other. Okay? Notice that there's a tiny little weird there's a little trick we do here. We actually have right here this integral f of x equal big F of x equals the integral from a to x of f of t dt. Note that this is actually a integral with a variable bounds. You can have a function defined as an integral with variable bounds, and we have to use f of t dt instead of f of x dx here, because otherwise this doesn't make any sense. our bound can't be um, the same as the value that we're integrating according to. So that's why the t shows up there. We just need a different variable to use. We could have used any variable. T is just the second most common um, independent variable. So um, this part of the fundamental theorem of calculus, while it is very important and it's a really important part of calculus, and it really is the first part of the fundamental theorem of calculus because it's the part you need to prove to get to the second part. It's not the part that we're actually going to use that often, and it's the part that people tend to forget, so this is a good one to have in your notes somewhere. The second part of the fundamental theorem of calculus is the one that you're going to use over and over again, which is that suppose, again, little f of x is continuous on a to b, and big F prime of x is equal to little f of x. So big F is a function whose derivative is little f, right? Then the integral from a to b of little f of x dx is equal to big F of b minus big F of a. And that's it. We can find the area beneath a curve using, if we know what function, if we know a function whose derivative is the function that we're taking the integral of, we can use that to directly compute the area beneath. And I really can't overstate how sort of miraculous this is. Miraculous is maybe not correct, but it's definitely a weird thing. We shouldn't expect this to be true in general, right? Like, why does the rate of change of the object have anything to do with the area beneath an object? And there's something to be said about what's called an accumulation function, right? If you know how fast something is moving and you know how long it's been moving for, you can get an idea for how far it moved. And that's sort of the idea here, right? So the big question that this should raise for everybody is, okay, so how do we find big F of x given little f of x? And that's what's going to segue into us into our next topic, which is anti-differentiation. And then we'll use that. That's the technique that we're going to use to solve integrals in general. Does anybody have any questions about the fundamental theorem of calculus before I jump into anti-differentiation? Okay. And can someone say something real quick? I've been having trouble.
Hello.
Okay, cool.
Yeehaw.
I've been having trouble where my Discord decides that it no longer wants to make audio happen, which is not ideal. So just wanted to check in to make sure that things are not broken. All right. So let's talk about anti-differentiation. So anti-differentiation is a there's a lot to it. One of the things that, so I posted in the off topic a little while ago. I posted an image about the processes of differentiation versus integration, and it's genuinely pretty true with differentiation. Finding these, there's only a couple of different things you can try. There's the chain rule, the power rule, the quotient rule, the product rule, etc. Once you've done all of those things, like you're done. Period. It gives you a complete picture. Unfortunately, integration is not so simple. Anti-differentiation is not so simple. There is no product rule. There is no quotient rule. There is no chain rule. There are some substitutes for those things. There's some techniques that are effective. In particular, substitution and integration by parts are two of the big ones, and so these are techniques that you'll learn through Calc 1 and Calc 2. In particular, we will do the method of substitution, U substitution, integration by parts, partial fraction, and trigonometric substitution are stuff you see in Calc 2. But we're going to start pretty simple, okay? We're going to start with essentially just deriving antiderivative formulas, right? So we're going to start with a really easy one. What is the antiderivative of f of x equals 2x? And I'm worried that I might have just lost sound.
I can hear you still.
Okay. Well,
I can hear you just fine.
yeah. What I'm worried about is whether or not I can hear you, which I can, so we're good still. Okay. Does anybody have any guesses what the antiderivative of 2x is?
X squared?
X squared.
Yeah, x squared. When we take the derivative of x squared, we get 2x. We've seen that over and over again. So if f of x is equal to 2x and big F of x is equal to x squared, then big F prime of x is equal to 2x. Are there any other functions that we could have chosen here? Or is that the only one?
Just different ways of writing x squared, I imagine. You can do x
Like
squared
what?
plus 0.
X squared plus 0. What about
If you like change the coefficient.
x squared plus 1? Does that work?
Oh.
Sure, that would work.
Yeah.
What about x squared plus pi?
As long as it's a constant.
Yeah.
Yeah. So here's our problem, is that given a specific function, there are actually an infinite number of antiderivatives. So given a specific function, there are an infinite number of possible antiderivatives. So we need to make some distinction between an antiderivative and the antiderivative. So there's a distinction between the antiderivative and an antiderivative. So the antiderivative, we're going to actually sometimes refer to this as the indefinite integral. I should put quotes around that. And when we're referring to the antiderivative or an indefinite integral, what we're looking for is we're looking for something that encompasses every possible one of these. So if big F prime of x is equal to little f of x, then the integral with no bounds on it, the integral with no bounds of little f of x dx is equal to big F of x plus a constant, where C is where C stands in for an arbitrary constant. An antiderivative is any big F of x such that big F prime of x is equal to little f of x. And typically when we're looking for an antiderivative, it's convenient to take the one that doesn't have a constant term on it, just so that we have to write less. So usually if we have a choice, we'll pick the one that doesn't have a constant. Okay. So to rephrase our example, let's find the integral of 2x dx. Well, that's going to be x squared plus a constant. Note that we also could have said x squared plus 1 plus c. But there's no reason to really bother with this. C, the constant that you get when you're doing integrals, it tends to eat up all the other constants, or rather you want it to eat up all the other constants. If c is constant, then 1 plus c is also constant. So we usually just write that still as x squared plus c. Technically, these two c's are different. Maybe this is a c1 and this is a c2, but again, we suppress all the other constants. So, and we roll up all of our constants into one big constant blob at the end. So going off of the previous one, we know what the antiderivative or an integral of 2x is, but what is the integral of x dx? Well, we know that the integral of 2x dx is x squared, and the integral of x dx is equal to 1/2 of 2 times the integral of x dx. And going back to one of our integral properties from before, this constant can come in and out of the integral. Constants can come inside and all the properties that don't have to do with the bounds for definite integrals also apply to indefinite integrals. So we can push this 2 inside, which is 1/2 of the integral of 2x dx. So this is 1/2 of x squared plus a constant. And once again, this 1/2 of a constant is still constant, so we're going to roll it in. So we're going to say that the integral of x dx is equal to 1/2 x squared plus c. Any questions about these two examples so far?
Maybe I just missed it. Where did the 1/2 times 2 come from?
My butt. So a half times 2 is equal to 1, right?
Right.
It was just my way of using the problem we did before to solve this problem.
Okay, so you're literally...
I'm saying I want this to be the
Okay.
integral of 2x because I know what that is already. But if it's going to be the integral of 2x, then I have to take half of that, right?
Okay, so the integral of x dx Okay, I got I got it. I got it.
Yeah.
It's another one of those multiply everything by one type situation.
Yeah, I'm doing a really weird way of multiplying everything by 1.
Okay.
Do you have a question, Adina?
Oh no, I was gonna say the same thing of the multiplying, like the strategic manipulation thing.
Yeah, it's a super common weird trick that we do all the time, right? Like sometimes, like if you go back to doing, if you looked at any of the proofs for the, like the product rule for derivatives, or a lot of them were like, I'm gonna add and subtract the same thing, right, in this clever way to do
Yeah.
this thing. So it's just one of those algebra tricks that we do when we're proving things. However, I'm gonna make that obsolete right now because I'm gonna give you the power rule for integrals. So we had a power rule for derivatives, and it turns out that we also get a power rule for integrals, which is nice. This combined with the properties of integrals is going to make integrating polynomials actually really easy. It's going to be a little tricky at first because you're going to get mixed up between the integration power rule and the differentiation power rule, and you're going to switch back and forth between them. It's going to be a giant pain in the butt, but eventually it should be pretty straightforward. So if n is not equal to -1, then the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus a constant. And this is kind of similar to what the power rule for derivatives is. So recall that the derivative of x to the n is equal to n times x to the n minus 1. Right? So to take the derivative of x to the power of something, we multiplied by the old power and then drop the power by 1. When we're doing the antiderivative, the reverse of the derivative we're going to do it in reverse. We're going to increase the power by 1 and then divide by the new power. Okay, so this integral power rule is the derivative one in reverse. So derivative what you do for the derivative is you multiply by old, then decrease power by 1. So the antiderivative you increase power by 1, then divide by the new.
Why doesn't it work when n is equal to 1? Shouldn't it not work
Negative
when n is
1.
equal to -1? Oh, okay.
Yeah, that's what it says up there. It does work when n is equal to 1. N is equal to 1 is what we just did in our example above, right? Note that this also, if n is equal to 0, then x to the n equals 1. So the integral of 1 dx, which is usually going to be written as just the integral dx. People don't usually write the 1 inside. That's just going to be, well, so that's the integral of x to the 0. So that's x to the 1 over 1, which is x. Or to state it more precisely and simply, the integral of nothing, the integral of 1, not nothing, is equal to x. plus c. I should have plus c's over here as well. By the way, you guys are going to forget your plus c's a lot, and I'm probably going to end up taking points off for plus c's missing. Be careful. Try not to forget plus c's. They're important. Whenever I'm asking for an indefinite integral, your answer will be an expression, a function of x, with a plus a constant on the end. Okay. The rest of the, well, actually, let's talk about what if n is equal to -1. That is, what is the integral of x to the -1 dx? Well, we certainly can't use the power rule. If we apply the power rule, we get x to the 0 over 0 plus a constant, which is undefined. So that doesn't work. Does anybody have any ideas what the antiderivative of x to the -1 is? It might help if you rewrite it as the integral of 1 over x dx. So what function has derivative equal to 1 over x?
ln x?
Yep. The natural log function conveniently saves us from this dilemma, right? So actually, the integral of x to the -1 dx is equal to the natural log of, it's actually the natural log of the absolute value of x plus a constant.
Could you scroll up just ever so slightly to the beginning of the problem?
That? Is that the beginning you were referring to?
Yeah, I'm just on Paul's online math notes, and it says n cannot equal -1. In this formula, we will end up with division by 0.
Yep. And then he says we'll take care of this case in a bit, and then I decided to take care of that case right now because it seemed relevant.
Okay, I misunderstood.
That's okay. So the power rule doesn't work when x is equal to -1. This is the exception here. This is how we deal with x equal to -1. Any other possible value, the power rule works. Okay, it could be x to -1.000000003, and you could use the power rule. But if the power is equal to -1 exactly, you have to use this formula instead. Okay. The other integral formulas that we're going to see are just derivative formulas in reverse. So in particular, we get the integral of e to the x dx is equal to e to the x plus a constant. The integral of sine of x dx is equal to negative cosine of x plus c. The integral of cosine of x dx is equal to sine of x plus c. So this is a little annoying because now it's the opposite, like, because it's the opposite, right? the integral of sine is now the negative one. The integral of cosine is now the positive one. My favorite way of sort of dealing with this is by doing my trigonometric integral clock. So sine x, cosine x, negative sine x, negative cosine x. All right. So derivatives go clockwise. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x, etc. And antiderivatives go counterclockwise. Actually, the British call counterclockwise anti-clockwise, which makes this work a lot better for people who are British. But nevertheless, clockwise for derivatives, counterclockwise for antiderivatives. You're going around in a circle like that. So if you remember the derivative rules, sine, cosine, negative cosine, you can just go backwards around that to get the antiderivatives. Similarly, we get that the integral of secant squared of x dx is equal to tangent of x plus a constant. The integral of secant x tangent of x dx is equal to secant of x plus a constant. The integral of cosecant squared of x dx is equal to negative cotangent x plus a constant, and the integral of cosecant x cotangent x dx is equal to negative cosecant x plus a constant. We just move the negatives over to the antiderivative side so that I'm not giving you the formula for the antiderivative of a negative thing. It makes more sense to have the antiderivative of the positive and then deal with the negative sign later on. There are also some forms that are very nice to see that come from our inverse trig stuff. We will not use hyperbolic forms, by the way. Our inverse trig functions tell us that the integral of 1 over 1 plus x squared dx is equal to arctan of x plus a constant, and the integral of 1 over the square root of 1 minus x squared dx is equal to arcsine x plus a constant. There is the arc cosine one is not so useful because the derivative of arc cosine is just negative the integral of arcsine. So I wouldn't worry about that one too much. It doesn't come up very often. And right now, these are basically the rules that we're going to have for a while. We're not going to be able to do a whole bunch of other stuff until we talk about the method of substitution. And right now, this gives us a pretty narrow range of functions that we could antidifferentiate. But it does give us some. For instance, this gives us all polynomials. I think I zoomed out at some point and I forgot to zoom back in. Yeah, okay. We're going to have weird margins on the notes for this page. So for example, let's find the integral of 5x cubed minus 10x to the negative 6 plus 4 dx.
Is there a difference between antiderivatives and integrals? Because it seems like you're using the terms interchangeably.
They're basically interchangeable. Antiderivatives and indefinite integrals are essentially interchangeable at this point because of the fundamental theorem of calculus. Antiderivative, I guess I should be a little bit more clear about that. An indefinite integral is typically solved through antidifferentiation. Integrals in general are a bigger problem. They have to do with that geometric area beneath the curve problem. Antidifferentiation is the primary technique for solving integrals that we use in calculus 1, 2, and 3.
Okay.
So hopefully that clears it up a little bit with regards to vocab. So here, what we can do, and you don't necessarily have to do this every single time, but I am going to break this down into some excruciating detail. We can actually push our integrals in a little bit, right? We can split up our integral over the different terms. So we get the integral of 5x cubed dx plus the integral of, minus the integral of 10x to the negative 6 dx plus the integral of 4x. And now we can pull out our coefficients as well. So that's 5 times the integral of x cubed dx minus 10 times the integral of x to the negative 6 dx plus 4 times the integral of blank dx. And now it's just a matter of applying power rules, right? That is 5 times x to the 4th over 4. I'm not going to write my constants right now. I'm just going to collect them all at the end. Minus... Actually, you know what? Let's write the constants. Why not? Let's say plus C1 minus 10 times x to the negative 5 over negative 5 plus C2 plus 4 times x plus C3. And then we can distribute some stuff and make this look a little nicer. We get 5x to the 4th over 4 plus 2x to the negative 5. The negative 10 and the negative 5 cancel out to a negative, or to a positive 2, plus 4x. And then we have plus 5c1 minus 10c2 plus 4c3. But I'm just going to say 5c1 minus 10c2 plus 4c3 is equal to just c. So our answer is really 5x to the 4th over 4 plus 2x to the negative 5 plus 4x plus a constant. Okay. The mucking about with constants here, where I did every single constant individually, if you really want to, you can do that. I'm not gonna like take off points for it, but like I sincerely hope that I never have to grade a piece of paper where you've done this, because it's really kind of silly. It's a lot of extra work. I think it's nice for you guys to see it at least once to note that like this is why we can group up all the constants at the end, because at the end of the day they all just come together into one big constant lump. You can basically ignore the constants until the end and slap on your plus c. Okay. The one place where this is going to come back and bite you in the butt a little bit is if we get to talking about differential equations, you need to be a little bit careful when you actually do slap in the plus c. But as long as you are, so as soon as you finish your integral, you just put a plus c on the end, then you should be good to go. Any questions about this guy? This example? All right. Let's take a swing at another example. Let's do the integral of 6x squared plus the square root of x over 2x dx. So this right here starts off as a bit of a problem. We don't have a method for doing a quotient rule. I just told you there's no such thing as a quotient rule. Luckily, I'm not going to give you impossible problems. I'm going to give you problems that are possible. And in this case, this is possible by simplifying, right? We can simplify this before we try to tackle it as an integral. And in particular, we can simplify it by splitting it up into the sum of two fractions. So the integral of 6x squared over 2x plus square root of x over 2x dx. And we can cancel and simplify these two fractions. Here the 2x and one of the x's cancels, and the 6. And here we can cancel out a square root of x. So we can rewrite this as the integral of 3x plus 1/2 of 1 over the square root of x. Much like when we differentiate something like 1 over the square root of x, we want to rewrite 1 over square root of x as a power of x. So we might even write this as the integral of 3x plus 1/2 x to the negative 1/2. And now we can just apply our power rules, right? The integral of 3x is 3x squared over 2. And the integral of 1/2 x to the negative 1/2, we're going to add 1 to the power. So that would be 1/2 times x to the 1/2. And then we're going to divide by the new power, which is dividing by 1/2. That's really the same thing as multiplying by 2 plus a constant. So that's 3x squared over 2 plus x to the 1/2. Or better yet, 3x squared over 2 plus the square root of x. Plus c. I had my plus c over there, and then I forgot to keep writing it. So previously, for derivatives, if you had that problem and you need to take the derivative of it instead of the antiderivative, you could have just brute forced it with a quotient rule if you really, really wanted to. It's kind of the messiest possible way of doing it, but it is a possible way of doing it. You do get an answer that way. However, here we don't have that choice anymore. You have to simplify before you can integrate. There's not another way of doing it. There's no quotient rule for you to fall back on. So the algebraic simplification is going to be important. The same thing for when you see products. When you see the product of two functions, you're going to need to multiply it out. You can't, there is no product rule that you can apply. Does anybody have any questions about these integrals? About the process of antidifferentiation as a whole? Okay. So I think that's where I'm going to leave it today for lecture. Little bit shorter this time. And I am going to give you guys some problems to work on. So essentially here, you guys don't have any tricky techniques. You're just going to simplify as much as you can at first, and then apply these formulas as they're written. Okay. Next class, we're going to get into the one actual technique of integration that we get in Calc 1, which is U substitution. It's kind of like a reverse version of the chain rule, but it's like way crappier than the chain rule is, so it'll be fun. It'll be great. So with that, I will assign some problems and let you guys go. Does anybody have any last questions before I let you guys go?
Thank you, Aaron.
All right.
Yeah, thank you.
As I said, I will try to get stuff. I'll try to get stuff graded up as soon as I can, and I will post out quizzes hopefully either today or tomorrow. So maybe tomorrow. I'm not sure.